All right, this is Mr. Jern, and I'm going to explain a little bit about AP Physics 1, Workbook 5K, as it currently is, Conservation of Momentum. So in this case, it is about writing procedures, which hopefully you're getting really good at. This Blake is given two carts of unequal mass, M and M, capital M, lowercase m, and a long track. Basically, just assume it's an infinite long track and it has zero friction. He also has access to other commonly available equipment. The carts do not have any way to connect together when they come into contact, so there's no Velcro or anything like that, magnets, nothing like that. He asks three questions. When the two carts collide, is the total momentum of the system conserved? When the two carts collide, is the mechanical energy of the two-cart system conserved? And when the two carts collide, is the force lowercase m of that lowercase m cart exerts on capital M equal to the force that M exerts on M? Okay, if you've been paying attention, this should look very familiar. A, you've probably done a lab like this. B, the previous workbook pages deal with both momentum and energy. They go hand in hand. They are not exactly the same. And sometimes they seem to disagree with each other. That's a simplification, but sometimes momentum is always conserved. And sometimes it seems like energy is not conserved, or there's external forces that do work. And so it can be a little confusing. Just remember, momentum is always conserved, and energy is conserved always unless there is an external force. Okay, that's just something to keep in mind. Momentum is always conserved, and energy is always conserved unless there is an external force that's doing work. So, outline a procedure that Blake could follow to make the measurements that could be used to answer all three questions above. Give each measurement a meaningful algebraic symbol and state with what equipment each measurement is made. Draw a labeled diagram showing each piece of equipment being used. Now, OAIM, object, action, instrument, measurement. If you use that system, you will do amazing with these, okay? These answers, the official answers, they don't necessarily use OAIM, but they have the same principles, okay? And if you use OAIM, you're gonna get it right, okay? What object are you acting on? In this case, it's the carts. What's the action you're gonna do to them? Won't mass them. You're gonna see it in here. You're going to put it on either end and track the motion. You're going to push the carts. That's your action here. What is the instrument you're going to use? Well, you're going to use a timer. That's a tool, right? The instruments are tools. What instruments you're going to use? And then going along with the instrument is, what are you measuring with those instruments? Okay, what is the actual measurable quantity? Remember, momentum is not something that's directly measurable. And so you can't measure it. You have to break things down into what is measurable. Velocity, we sort of kind of cheat a little bit with our equipment. Even it looks like it's allowed in AP, like you can use a motion sensor to find the velocity. But velocity, if necessary, and if you're not sure, you can actually say measure the distance and the time, and then you could calculate velocity, which is exactly what the motion carts do and the sensors do. They measure the time, and they know the distance that the carts go. So, but you can cheat a little bit on the velocity, measuring the velocity or graphing velocity as a function of time. See, that's what this did here. So it might not be a bad idea to really mention the fact that velocity also has to be calculated, and it's the safer way to do it. Okay, so these are okay, so what are you going to find? Well, you got to find velocity. All right, you also will get the mass. We'll get to the diagram in a moment. So you have to get the mass each cart. Okay, that has to be done. And I don't recommend you use these words. That's why I don't put OAIM here. I leave it as the default official answers, because I want you to practice using OAIM, object, action, instrument, measurement. Okay, so That's not a bad idea to do that. Look, you could look at this, but maybe translate it into OAIM, okay, for yourself. But what do you need to do? You need to get the mass. You need to tell it what you're going to do. You're going to set the carts in motion and track them somehow with a motion detector. Now you got to be careful because we use magic carts. It seems like they're magic anyway. But remember, what are these motion carts measuring? Okay, why do we use them? What are we getting out of them? Okay, right. So use a motion detector, use a tool, use the computer, use a sensor, right? But keep in mind and mention in your instructions, what are you specifically measuring? Some kind of motion detector. Don't just say use vernier graphical analysis to blah, 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 blah. Okay. No, use the sensor that's in the cart or wherever. Like in this diagram here, they have external motion sensors. Okay. We used that a long time ago, and you can use that. But the bottom line is you have to use reference the sensor, not the computer. Does that make sense? I hope it makes sense. If not, let me know. But so the app that we use that presents the data is not the sensor. So mention the sensor that's doing the actual sensing. All right. So motion, in this case, they have motion detectors to record velocity. You can say use the sensors on the cart to detect velocity as a function of time, but make sure you're doing that. And then you have to do something, you got to push the carts. And then you have to explain how you're getting stuff. Graph velocity as a function of time for each cart. Okay, what's that going to do? Well, it's going to give us acceleration later. Okay, well, why do we need that? We're getting there. So here is a diagram. Make sure it's labeled. See, now we haven't used a system like this in this class, in our class, to get measurements of our carts. But I hope, looking at this, can see how this would work. Okay, and that's the important thing. Now, you don't have to say this exact setup. This is an example, but this is an example that you probably haven't done. But that's the cool thing, is by looking at this example, you could probably imagine how it would be done if you had that equipment. And that's what you need to do. You need to explain it in such a way, and that's your audience, is people like you who maybe have never done this exact lab before. But you can look at this and you can actually repeat it if you had this equipment. Okay, that's your goal. Okay, now you've got mass and velocity. Now what? And time, and you graphed it. So now to answer question one, what was question one? Okay, sorry, I'm scrolling back and forth. It's probably nauseating. When two carts collide, is the total momentum of the system conserved? Okay, well, what do you need to get momentum? Mass and velocity. So the mass has been measured and recorded, done. Mention that. Explain how the measurement's made. Okay, what are the measurements? Make sure you mention what they are. If the momentum is conserved in the collision, then the momentum before, blah, 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 okay, we got all that. We know all that. The motion detectors create a graph of velocity as a function of time. Okay, so we're referencing the fact that we've measured velocity now. The velocity of each cart before and after each collision, you're getting it off the graph. And then it says, to answer the question, so is momentum conserved? So you have to actually include this equation, because that's what you're going to be comparing. The masses and velocities of the carts before they collide, and the masses and velocities of the carts after they bounce off each other. Okay? Number 2, explain how the measurements in part B can be used to answer the question 2. All right, sorry to scroll up again. When the two carts collide, is the mechanical energy of the two-cart system conserved? So once again, think about the mechanical energy of the cart system. Do they have potential energy, gravitational potential energy? No. They're not going up and down hills. Do they have elastic potential energy? No, there's no springs involved as far as we could tell. So that must mean it's only kinetic energy. Well, that means you need 1/2 mass times velocity squared. So you need mass and velocity. So once again, explain, you've got mass measured. It talks about the kinetic energy before the collision and after the collision has to be equal. The motion detectors can create a graph of velocity as a function of time. So boom, there's our velocity again. And then the equations, they should be equal. Okay, check for equality. Is the left side of the equation, the before they collided, equal to the right hand side of the equation? the part after they collided, the energy, total energy of both carts after they collided. And are they equal? Finally, question 3, one last time. Is the force exerted on, the force is the same essentially. So one last time. Now here's why we got the graph, because what is force proportional to? I guess I'll use that word. It's a good word. Well, the masses don't change, and so the force will be proportional to the acceleration. And so you have a velocity versus time graphs. How are you gonna get acceleration? Well, the slope of the velocity time graph is going to tell you acceleration, and so you can compare the slopes of the carts to get and multiply them by the mass of the carts, because you do have to compare. You have to include those, and then you can figure out the forces on each cart to compare them. Okay, so once again, what are we doing? We need acceleration. We've got the masses. What are we doing with those? We are going to multiply the acceleration, which we got from the slopes, times the masses of the respective cars, and we're going to compare them to see if they're the same. And that answers the final question. So hopefully that helped. I know that last one was a little confusing. Just look over it again, try it out, maybe plug some numbers in. But again, how would you have gotten that? That's the tricky part, because I bet it makes a lot of sense me explaining it, but would you have gotten that on your own without me explaining it? And when in doubt, look at the equations. Here, one last thing I'll say about that, because would you have gotten that without this explanation? A lot of people might not have. But how did you get it? Well, forces are not mentioned in energy. They're not mentioned in the energy equations. Forces are not mentioned in the momentum equations. So what do? When in doubt, look at your equation sheet. Where are forces mentioned? Oh, not even kinematics. It's in the Newton's second law equation. Force is mass times acceleration. Acceleration is mass divided by force. So how did we know we had to find the slope of the graph? Well, it's asking for force. And the only way to get force, look to the equations. Oh, I need acceleration. Oh, we have the masses. We got the masses already. I need acceleration. How am I going to get acceleration? Well, we have velocity and time. Let's graph it. We get the slopes. Oh, do you see? So look to the equations, and that'll help you figure out what you need to do to what variables you need in order to solve for these things. All right? It ain't easy, but that's why we do these practices. All right, I know you can do it.